Good morning, everyone. I would like to present the software tool demonstration for predictive models and sampling plans. This software was generated within the baseline project, and I will describe the main features during this presentation. This is the outline. First of all, I will describe the risk analysis approach to meet industry needs, and I will go through the source and development of the software and the different modules, such as predictive models, the optimization of sampling plans, the derivation of microbiological criteria, and also explaining the tools and decision support system. When the Regulation 178/2002 came into force, food safety should be quantified by following a risk analysis approach. In this slide, I present the main components of a risk analysis approach, which consist on different phases such as risk assessment, risk management, and finally risk communication. This approach was further adopted by several international organizations such as the FAO and WHO. Regarding risk assessment, it is defined by the scientific evaluation of known or potential adverse health effects resulting from human exposure to foodborne hazards. It consists on 4 different phases: hazard identification, hazard characterization, exposure assessment, and risk characterization. The main information that can be used by food stakeholders or food operators mainly comes from the exposure assessment approach, in which the microbiological concentration at the end of production can be quantified. From this approach, it should be some components that can be set. For example, this risk assessment should be transparent. In other words, it should be mention all the information in the documents. They should be a science-based approach, a quantitative approach. We intend to quantify the microbiological evolution throughout the food chain. It should be based on a systems approach by defining step by step the microbiological behavior, and also predictive models can be used as a tool to quantify this microbiological behavior, as I will show later on. Other documents, other organizations arise from this approach, from the risk analysis approach. For example, the famous white paper on food safety in 2000, and also the European Food Safety Authority, which elaborates scientific opinions. Also, regulation framework can be described, as well as food policy strategies or food control programs. In the meanwhile, the food industry, the food sphere, is waiting for adopting this kind of decisions, but in many cases this information is not so clear to be adopted in reality. To do this, there are some tools that can be used based on quantitative approach. For example, validation of preventive measures can be set by following the ICMSF equation, which is described here. In this equation, the food safety objective, in other words, the maximum frequency of concentration of a foodborne hazard at the moment of conception, should be lower or equal than the sum of the initial contamination of the raw material and the sum of reductions and the sum of increments of the microbiological pathogen in the food. To achieve this equation, there are some models that can be used, but in many cases there is a lack of experimental data, of new experimental data, and also uncertainty sources cannot be quantified properly. Transparency is also very important, because this process should be very well documented, and it should be an interaction between the different elements and components. In this sense, preventive measures should be based by following a hazard analysis and critical control points approach, and also by using the predictive microbiology. This science-based predictive microbiology can be evaluate these different scenarios. For example, assessing the conditions, assessing the relationship with the output, the risk, and finally by studying cause-effect processes. For example, a pipe-like crack can lead to a leakage or dripping, and finally the biofilm formation and salmonella can survive or growth. This behavior can be quantified by using the different predictive models. But what is predictive microbiology? This is a microbiological area that studies the evolution and behavior of microorganisms in food. This is very well related with food microbiology and microbial food safety, and also with the setting of the HACCP, process control, and also the microbiological risk management. In this sense, predictive microbiology is based on this hypothesis. For example, the microbiological analysis. In many cases, there are inaccurate, there are also variable, it can lead to obtain a variable result. Also, these analyses are costly, and there is not always a good result. The use of mathematical models with a certain simplification degree constitute an appropriate tool in many cases by which accurate estimations can be obtained about microbial responses of different processes throughout the food production chain with less resources consumption. In this case, by using this kind of predictive models, the user can quantify properly the microbial behavior in foods without performing different microbial analysis. This is predictive microbiology, and of course, from the 90s, there are some publications that are published. More than 400 papers in international journals were published about the predictive microbiology, but of course, it would be still very useful to facilitate their use or their application by final users. There are some elements that can be derived directly from a risk assessment methodology and can help the food industry to ensure food safety. One of these elements are the microbiological criteria and its derivation, and also the control limits, process parameters, and also the risk-based metrics. Some examples are shown at the right side. For example, to establish a shelf life determination based on growth predictions, supporting decisions where data are not available, for example, at low levels after an inactivation process, to establish rapid response tool by performing in silico models or in silico estimates, and finally validating control measures. This microbiological criteria is one of the key elements to be applied by food stakeholders. In this sense, these microbiological criteria can be set at a specified food chain step, and there are tools that serves to verify acceptance or rejection of a given food lot. To derive these microbiological criteria, or better said, to facilitate their implementation, it is very useful to know how microbial contamination is distributed into a food matrix to define the correspondent risk-based metrics like the performance objective. In this sense, the stringency of sampling plan is defined by the parameters n, c, and lowercase and uppercase m. The stringency increases at a higher number of samples, a lower value of c, and a lower concentration and frequency limits, and also by increasing the sample size. But when high variability in the contamination is obtained, which is the most common case in a lot of foods, in a wide range of foods, the confidence level target is higher, a more stringent sampling plan is normally required, so that in many cases is not, cannot be achieved. The establishment, to establish the risk-based metrics, it is highly important then to know the microbial distribution of the contamination and the prevalence within a lot and also between lots. There are some information sources that can be collected. For instance, it is needed to know the concentration or maximum allowable level, the maximum percentage of the effective units in the lot, and also the information of the parameters of the microbial distribution and the analytical technique that is followed regarding its sensitivity and specificity. The first two information sources must serve to derive also a performance objective. But with this information, it would be very useful to easily derive these microbiological criteria from established FSO or PO to facilitate their implementation in food industries. These were the basis by which a baseline software tool was created. The baseline software tool allows both to predict the microbiological behavior with validated predictive models and also to derive or to establish microbiological criteria. The software tool is a free access and online platform. It consists on a graphical user interface with different tables and graphs. It's very intuitive, and also the tool is characterized by its flexibility. For example, new models can be incorporated as long as new data are being gathered. And also the tool can facilitate a comparison and scenario analysis studies to evaluate the effect of different variables on the microbiological behavior in a specified food matrix. The free registration is available at this website. So again, as I mentioned above, the software tool allows to predict growth and inactivation of different microorganisms in different food matrices, and on the other hand, to design and apply sampling plans in different food categories. Now, in the models module, there are 75 predictive models that are already implemented in the software. Some of them were collected within the baseline project and generated with the baseline data, and the other part were gathered from literature data. There is also a sampling plans module that allows users to help or design efficient statistical sampling plans by taking the smallest number of samples necessary while providing the largest confidence possible to detect a non-conforming lot. In other words, to optimize the sampling schemes to be used in a practical way. Regarding the predictive models module, there are different types of models that are included in the software. Basically, there are primary models of growth and inactivation models. The main functions are the Comport function, the Barangian-Roberts, and three-linear phase model. And regarding inactivation models, there are the linear model and the Weibull models. Finally, the secondary models, there are common structures that are already implemented in the software, mainly the Rutkowski type and also the polynomial models. Also, cardinal models can be implemented in the software by including the appropriate cardinal parameters. So, the key message is that these mathematical equations, apparently complex to be used by food stakeholders, can be integrated within an easy-to-use software. This was the main feature or the main idea by which this software was created. I will explain right now the previous stages by which this software was performed. First of all, we proceed to identify the main food matrices, basically the 5 food categories that are included in baseline: seafood, egg and egg products, milk and dairy products, meat products, and also plant products. Then we identified the main microbial hazards associated to each food category, mainly Vibrio parahemolyticus, Listeria monocytogenes, Vitek, Campylobacter, and Salmonella. The third step consists on identifying the specific environmental conditions in order to develop specific predictive models. The fourth step consists on a literature review of the available predictive models in literature. When data gaps were found, we proceed to gather data from the project, from the baseline project, and to develop a new or alternative predictive models. there were several databases that were revised, and more than 100 scientific references meeting the proposed requirements, and we selected these references according to different criteria that were previously defined. The final step was the implementation of these predictive models into the software. To do this, in this dialog box, you can see the different fields that by which a predictive model can be included in the software. This platform allows users to add or to edit or even to remove predictive models that are already implemented, and also as long as new data are being available. In this case, you can set here the reference, the type of model, type of food and risk combination, to give some details, the time unit, and in the right side you can select the appropriate kinetic parameters and include the environmental factors that this model is going to predict. So there is an easy implementation of these predictive models, mainly in HTML format. The user can allow, advanced users in this case, are allowed to add or to include these models in the software. This is an illustration where you can find some predictive models. In this case, the software allows a multiple comparison. Up to 5 models can be compared in the software, and I will describe briefly these windows. The left part, the left side, there are the raw data that can be exported to Microsoft Excel or to another file for further use. In the central part, you can see the graphs where you can estimate the microbial behavior at the specified conditions. In the right side, you can see the different food categories, and also you can filter the data according to the type of microorganism. You select easily the type of the predictive model to be applied, and graphs and raw data appeared in the window. In the bottom, there is the main information that can be collected from each predictive model. For instance, the food matrix, the type of model, primary as well as secondary, the kinetic parameters, and also different actions such as the model's validation, the model's edition, and also to remove or to add models and some extra information, and even to change the color of the graphs. This is the validation module of the software. When new data are being available, this data can be compared with the predictions of these predictive models in this validation platform. For instance, if I would like to validate a specific model, I select the kinetic parameter and the environmental factor to be validated, and manually I insert the different data regarding this kinetic parameter. In this example, I show a validation of the maximum growth rate as a function of storage temperature. You can see here 2 different types of graphs. In the upper graph, you can see the equivalence line is represented by the green line, and the observed data points, which are those colored in red. From this graph, you can compare the predictions of the model with the observations. These are validated by the different validation indexes: the standard error of prediction, the root mean square error, the bias factor, and the accuracy factor. These are the raw data, observations and predictions, and in this graph you can see a relationship between the kinetic parameter and the environmental factor. This graph, and also the other one, can be downloaded in different formats. This is the exportation of the data of the software to Microsoft Excel. The data can be exported easily into a CSV file, and also a report can be created from the specific predictive model that are being applied. Regarding the sampling plans module, there are different concentration or attribute sampling plan. In this case, I present the attribute sampling plans, which are mainly the binomial distribution, the Poisson distribution, negative binomial and trinomial distribution, and the concentration-based sampling plans, which include the log normal and the Poisson log normal distributions. In this case, I show you an example about the performance of a log normal distribution to accept a specified food lot at a 95% confidence level. The user can easily select the type of distribution and also the parameters of this distribution, and to derive here the sampling plan. This is a two-class sampling plan in which I specified the mean concentration, the standard deviation, which represents the variability of the food lot, the microbiological limit, and also the number of samples and the maximum allowable number of samples that cannot exceed the microbiological limit. In this case, you can see two different graphs, the cumulative distribution, descendant cumulative distribution, which gives directly the probability of acceptance of this sampling plan, and also in the right side you can see the density distribution. In this case, the user can compare different sampling plans in order to achieve a specified probability of acceptance. There are some practical examples that are included in the software based on prevalence and concentration data. I will explain briefly both of them. First, I will explain the establishment of a microbiological criteria from a performance objective that is set in prevalence terms. This is the practical example. By this example, the user can decide the maximum allowable contamination rate and also the specified confidence level that is deemed as appropriate. The user can set the number of samples taken from the lot, and the software immediately gives the information about if this number of samples is or not enough to accept the lot at the specified confidence level, and also how many samples should be needed to accept the lot. In this case, there were 24 samples to be taken to accept the lot at this specified confidence level, which is usually set at 95%. In this graph, you can see here the blue vertical line, the number of samples that would be needed to accept the lot, and in the red vertical line is the number of samples that are taken from the lot. This is the other example. I will explain very easily how to derive a microbiological criteria from a performance objective that is set as a concentration value. This is the second practical example where the user can set here the maximum allowable concentration that cannot be exceeded, as well as the maximum allowable proportion of units that should not be contaminated. In this example, I assume that no more than 99% of units would have a concentration higher than 4 logs. Below, the user can set the parameters of the microbial contamination of the sample. In this case, I assume that the sample will have a concentration of 2 logs with a standard deviation of 1 log. In this example, the software gives information about if this distribution can or not comply with the specified performance objective. In this case, this distribution cannot comply with this performance objective, as 97% of the units will not contaminate it. As we said, 99, we should apply a corrective measure. There are different corrective actions that can be applied in the software, for instance, to reduce the mean contamination of the lot, to reduce also the variability or the standard deviation. We can even assume the obtained reduction And finally, we can increase the target value for the log acceptance. In this case, the most common corrective action consists on reducing the mean contamination of the lot. Let's see what's happened if we reduce the contamination from 2 logs to 1.5 log. In this case, this distribution complies with this performance objective, as more than 99% of units will not be contaminated. In the last part, we can derive very easily the cumulative distribution, in which we can observe in the green vertical line the performance objective, and in the red line where we can see the mean concentration of our distribution. We can set even a microbiological criteria. We can derive a microbiological criteria from this established PO. In this case, the software allows the user to introduce the microbiological limit and also to set a sampling plan, to introduce the number of samples and the maximum allowable number of samples that cannot exceed the specified microbiological limit. In this case, the probability of acceptance of the sampling plan is equal to 0.03. So, if it's lower than 0.5, 0.05, this microbiological criteria complies with the PO selected at a 95% confidence level. By this model, or throughout this model, food stakeholders or many users can set, can optimize, or can design new sampling plans and microbiological criteria directly adapted to each food processes. In this case, for this example, this would be the microbiological criteria to be applied. There are some specific sampling plans that were developed within the baseline project. This is one illustration of a specific sampling plan, in this case for Campylobacter in poultry carcasses. You can find information about this sampling plan and also the main graphs, the cumulative graphs, the density graphs, and also you can export this sampling plan into a PDF report if necessary. Finally, there are some tools such as the decision support system. This was created to help to non-experienced users to select the most suitable options to design sampling plans. This is based on yes/no questions regarding prevalence, concentration, and the different processing conditions. If we know beforehand how our microbiological hazard behaves into our food matrix, we can derive the most suitable option to be used in the software by following the different questions from the decision support tool. For this case, this decision support is mainly oriented to non-experienced users. These are only some of the main features of the software, but there are many more of them. But as a concluding remarks, the baseline software tool predicts microbial behavior of different pathogens and food matrices with validated models, makes possible the addition of new models or even new sampling plans, as well as data being gathered, provides an easy derivation of microbiological criteria and sampling plans from previously established risk-based metrics, offers a tools menu to perform scenario analysis if we intend to evaluate, for instance, the effect of the sampling size, increasing the sampling size, the effect or the impact of the analytical technique, the number of samples. And finally, the software includes this decision support system to help non-experienced will to choose the suitable option. To do this, I will finish my presentation, and I would be very pleased to answer all your questions. Thank you for your attention.